In the next part of computer architecture, we have seen previously about the addition and like how to convert the numbers from decimal to binary, binary to decimal, number about the basic number systems, and how we can calculate the complements: 9 complement, 10 complement, 15 complement, 16 complement, and n complement and n minus 1 complement as generalized format. So in the next section of this video, we will see how we can represent fixed point representation. Like there are two representation: one is fixed point representation, another one is floating point representation. So let's start. So if we are given a basic number, like here I taken 7, so how we can calculate 7 to, like, it is in decimal, so we have to convert it into binary format. So how we are doing it, we just like in the previous lecture we have seen how we can convert it. So it is converted into this part, like 0 1 1 1. So we can see how we can convert it, but the problem is when there is minus 7 is given, like you can say there is like 7, so 2 divided by 7, that is 3, and then there is 1 2 1 1, and there is 2 1 1. So you can say it is 1 1 1. So why there is 0 1 1 1? So we are representing in 4-bit format first of all. Second of all, if there is plus, you can represent it as 0 1 1 1, or if you can say that we are representing it into 4-bit format. Okay, or you can also say that we are representing the number in form of like 0 is representing the sign of the number, and 1111 is the actual magnitude of the number. So for fixed point representation, for fixed representation, if it is given with the sign 2, then plus is represented by 0 and minus is represented by 1. So let's see how we can get the value of minus 7. Okay, so first plus 7 value has been taken, then one's complement is being done. So in one's complement, what we are doing, we are making all ones to 0 and 0 to 1. So there is like 1000, that is the ones complement of 0 1 1 1, and then we are getting the twos complement. So to getting the twos complement, we just have to add 1, and we are getting to the value that is 1001. So it is the value of 2's complement. Okay, so here how it is calculated, and every time do the fixed point representation in 4-bit format. So I hope it is clear. So it is the easy part of representing a number, and there is like addition, subtraction, and overflow. Maybe I will make a video on it. It's not sure because there are more important topics than this, but I will touch it, not completely but slightly. So then there is like floating point representation. So there is a format named IEEE 754. So it is a widely like accepted format to representing a floating number. What is floating number? That is like 2.3. How we can represent this binary number where there is a decimal point to our binary code. So there is a fixed type of representation that we have to do, that is IEEE 754. So let's see how we can do it. It is easy, but I have taken a complex example that you understand it well. You generally don't get this type of big examples in your examination, but I have like make you understand this, that you get used to it, and in exams that seems to be very easy. You will generally get a small number because calculator are not allowed in same exam as far as I know. So you will get a small number like 56, 76, this type of number you will given. I have taken a big example, just bear with me, I will make you understand, and don't go deep into my calculation. It can be wrong because I have to do it very fast, so please bear with me. So first step we have to do, that we have to differentiate the numbers that is before points and after points. So first we have to calculate the part that is before points, and then we have to calculate the numbers after point, and then we have to add them. Okay, so first we have to see that is before points number. Okay, so let's handle with that. So here how we do it, like normal process, that we are converting decimal to binary, that is whole the process. You take the number as you wish, take a small number that you grasp through it and familiar with how the process is going through. Don't take this big example, it will take you some time. I initially don't understand that it will take time to calculate it, but after that I realized that it will take some time. So yep, take a number, then divide it by 2 until you get 0 and 1 as like answer and remainder. So from that you will get the binary code. Okay, so here we follow bottom to top approach. Okay, then the number that is after uh, decimal points, that we have to handle with. So here the number is written, that is 0125 here as it is given. So 0125 into 2. So in floating point representation we are converting decimal to binary only. Okay, if it is given like hexadecimal, don't fumble upon, like just do it in same process, change the base, and if you want like more easy way, then just convert it into decimal, and then the process is still same. So yep, so here we have to multiply it with the base. Okay, 2 is the base of binary, so here we have to multiply it by 2 only, or the base only, till we get to a whole number. If we get a whole number as product, then we have to stop. Okay, that is the first condition. And the second condition is, if we cannot get a whole number after repeated repetition, that I will show another example, and the pattern is repeating itself afterwards, so then we have to stop. Okay, so yep, I am clear, I guess. So here we are multiplying it, getting the answer, then we multiplying it again after getting the answer, and then we multiply again and get 1. 1 as it is a whole number, we have to stop here. Okay, then we have to take the last digit. Okay, the last digit of the number, so 0.2 250. So the last digit is 0, so we are taking 0, then there is like 0.500, so we are taking 0, and then there is like whole numbers, so we are taking the initial value of the whole number. So that is the only convention you need to remember. After that, here it approaches like initially when the number is before points. So the number before points, we are taking the normal approach, but for the numbers that is after points, we are taking the opposite approach, that is top to bottom approach. Okay, so here we are converting the whole number, like writing it wholly, completely in binary format. Okay, so like normally it is written in this. So it is the step 1, we have to convert the decimal to binary, first step. Second step, we have to normalize it. Okay, so this is the step 1, and then we have to normalize it. How we can normalize it? We have to normalize 1.n into 2 to the power something. Okay, so what is n? Okay, we understand what is 1. So here it is given the first number is 1. Okay, so we have to give a point after 1 in the next step. So step 1 is done. So in step 2, what we have to do, we have to give a point after 1, and then calculate how many numbers are there before points. So like after 1, how many numbers are there before this decimal point. Okay, so as we can see, here is like 1 2 3 4 5 6 7 8 9 10 11 12. So I guess there is like 11 or 12 numbers. So calculation is somewhat wrong around, so I have not rechecked it. So there is like uh, let's suppose there is 11 numbers. Okay, so after point, don't take this don't take this and don't take this. So you have to exclude the 1 and the number afterwards point, so you have to exclude that and have to calculate the numbers before after 1. Okay, so here is another thing you have to remember, that is you have to exclude 1 and exclude the part that is after points, and then you have to calculate how many numbers are there. You got that? So you have to write like 1 point and afterwards things, including this 001, that is after points, you have to write that, and then you have to give multiply 2 and 2 to the power how many numbers you have calculated. So I have calculated, let's suppose there is like 11 numbers. Okay, so let's suppose there is 11 numbers. So let's suppose there is 11 numbers from here to here, so we have to give 2 to the power 11. Okay, and your question is done now. So you have to follow another some steps, but that was the main point you have to do. Okay, so this point is called, this step is called normalization. So normalization is being done, so go to the next step. If the number is positive, so here we can clearly see the number is positive enough. So yes, so for positive numbers, as I say, you have to give 0. So we in IEEE approach, we use SEM approach. SEM, you are giving semesters, so SEM, that is sine, E for something, M for mantissa. Okay, so let me explain what is E, what is S. So S signifies a sign. If it is positive, we are using 0. If it is negative, we are using 1. So you got that. Then there is E or E dash, you can say. So E is E plus bias. What is E? How many numbers are there? You have counted. So you have counted, there are 11 numbers, so 11 plus bias. So we have to calculate the bias. So to remember the bias, so there is like two type of floating point representation, one for uh, 32 bits and another one is for 64 bits. Okay, so there is two type of precision points, or we can say for bits. It's like a, what I can say, system that you have to follow, that in question it will be given, that is you have to calculate for 32 bits or 64 bits. So for 32 bits you have to add and it is the bias. Okay, so the bias is 127 and another one is 1023. So E is 11 as we have calculated, plus bias, that is 127, and it came to be 138. And for 64 bit, it is for 32 bits and it is for 64 bits, as I said previously. Okay, so for the next step, what we have to do, exclude the mess please, I mean bear with it. So here the number came to be in decimal points, then we have to calculate it into binary numbers. So yes, we are converting the decimal numbers to binary in the normal format. So yes, we are doing it. So we are getting the binary value by normal process because there is no points and all. So then there come the representation approach, how we are doing it. So there is S, there is E, and there is M. So M is mantissa, E is exponent, yes I remember it finally, and S is sign. So the sign is positive and negative. So as it is positive, we are giving sign 0. So sign bit is always 1. For 32 bits, it for 32 bits. So for 32 bits, exponent should be 8 bits and mantissa should be 23 bits. If you add them all, you get 32. So that is how 32 bits representation are being done. And if you like do the maths properly, you will get 8 bits. If you don't get 8 bits, just add some zeros afterwards. Okay, because afterward if we add 0, that has no values. Right, so you get that. So E is exponent is given and it is like 8 numbers, so it is 8 bit. If we get like 1010, that is 4 bit, but we have to complete the 8 bits. So what we can do, we can add 0 and like this. So if you can see, if there is 4 bit answer we are getting, by a small number, let's suppose. So if we are getting some small number, so like 4-bit wala number, and we have to make it 8-bit, we just have to add some zeros afterward. You can like give dot dot and zero, that will signify it. So for 23 bits mantissa, we have to do that. So what is mantissa? So if you remember, in normalized form, the numbers all after the point in step 2, of course, where we are doing like into 2 to the power something, and something is number that is we have counted after 1 and before points. So in that step, mantissa is the numbers after the points. So these are the numbers that is after the point, so it is the mantissa, the whole number is mantissa. Okay, so that we are giving in mantissa, and we are adding dot dot zero because 23 bits are not covered, but we have to write it like 23 bits are covered. So dot dot zero signifies where the empty spaces are there, it are completed by the zeros. So same we are doing for 64 bits, because here is a e, that is exponent for 64 bits. So just we have to convert it into the binary, then what the value we get, we have to give it to the e, and e will be filled. If it is not filled, okay, so for 64-bit it is 11, or sign bit is always 1, it can be given short questions. Exponent bit is 11, and mantissa it easy, it is, remember this sign bit is always to be 1. Okay, sign bit is not, like sign bit is always 1. For mantissa for 64-bit, it is like previously we have studied 23, we just have to like mirror image of it, that is 32. So the mantissa should be 32 plus 23, that is 55, I guess. So yep, it is 55. 55 plus 11, that is, okay, so it come to be big. Just forget. Just remember that it is the mirror type of it. That is uh, 32. The mirror image of 32 is 23. So yep, you got that. And then the mantissa is still same. The only thing are changing is exponent. So what the exponent, you get the value. But if it is not covering 11, generally it should be covering 11 bits. If it is coming like 101010, so it is like 6 bit. So to cover it, you have to add 5 zeros. So you write like dot dot zeros, and it will be covered. Then the mantissa you should add, and so it is done. And then there is like, let's suppose in the question that is given like 2.3 is given, so we have to convert it. So in the first part is easy, that is we are just uh, so it is easy, that we are just calculating it like this. If I'm not wrong, that is, I mean, here it should be 0 2 0 1. So here how it is being done. So first part is 10, it is 10. So first part is 10. So yep. So how we can calculate the afterwards, there is like 0.3. So we have to multiply it by 2, the base, so that come to be 0.6. We are multiplying 0.6 into 2, that is 1.2. Okay, 1.20. So you can write like this, it's like good format. Then there come like 1.2 into 2, that is 2.40, and 2.4 into 2, that would be 4.80, and it should repeat itself. Okay, so